So I use the term compute, and I will make it a little bit more precise during the talk. I hope it becomes completely precise. The algorithm does not use branches where it is not absolutely necessary. The algorithm has to be interpretable in numerical analysis, so it has to be continuous, and some other properties which I resume in programmable by software engineering. So the inputs of our computation problem is given by H is given by a arithmetic circuit, and what I want to find is another arithmetic circuit, which I can compute from the values of H on the graph. Now, we proved the following result. If I want to solve this task, this goes necessarily wrong. So the output circuit for H, which I obtain in this way, is necessarily exponential. For any algorithm which computes solution for my problem, it requires necessarily exponential time. Because my polynomial class O consists of polynomials which are something easy to evaluate. This means the evaluation complexity is logarithmic in that degree. We may conclude that there are polynomials which are easy to evaluate, but which are necessarily hard to interpolate. So the output side, the interpolating circuit, becomes necessarily exponential. This I may also interpret in another way, that if I consider the easy polynomials as a concept class, each easy polynomial will be then a concept, then these polynomials are hard to learn. I have to say something about my notion of learning. I use here a notion of correct learning of concept classes, I work in the continuous model. This is a difference to the pack learning model, which is in the Boolean setting, which means probabilistically approximatively correct learning, and uses the notion of approximative learning. In the corresponding result, in fact learning theory, it is an open conjecture, which can only prove modular hypothesis in, for example, conjectures in cryptography. Now I want to go to another example. We look first to this class of polynomials. As in the former case, what you have to retain from the polynomial is that it has a concrete form, and you can evaluate it easily. Then you consider this class of polynomials, which I'm going to explain now how it appears. You see that if you put t equal to 0, you get the famous polynomial, which nobody knows. But since Euler's times, what is the complexity to evaluate it? This is some deformation of the polynomial. And there is a relation between two polynomials. There is a map which is defined in the language of C and is continuous with maps the polynomial H to the polynomial F. And this comes from the following situation. Look here at the hypercube as a solution variety of this equation system. We look at this as a subset of C to the n. Then H maps C to the n to C. And this map H maps just this set on this set of complex numbers. So, in other words, if I look at this first order formula, then which contains existential quantifier, this formula, this quantifier-free formula, defines the same set. So the polynomial f realizes a quantifier elimination, and in this sense we say that f is the elimination polynomial which is associated with this equation system and a map H. Now we put this in a more algebraic setting, so this parameter u and t, we replace them by indeterminate. We look at this polynomial, and we think that this polynomial is given by a arithmetic circuit of size O to the n. And f with the corresponding elimination polynomial, and now the task is given beta, find an arithmetic circuit beta prime which represents this elimination polynomial. So, big problem. The beta prime is a circuit which beta is a circuit, a given circuit to both sides O to the n that represent this polynomial, and what we want to compute from the circuit beta, a circuit beta prime, which represents this polynomial. Now, in the sense that as before we want that this algorithm is robust and it's programmable using software engineering rules or respecting software engineering rules. In particular, the variables T and U are hidden, and all information which depends on the coefficients of the input polynomials is used. Then, in this setting, we can prove that this again goes wrong if I require that my algorithm can be implemented respecting software engineering rules, then the output circuit is necessarily of exponential size. We can also, in the sense of before, formulate this in an alternative way, that the concept class of elimination polynomials is hard to learn, even if the elimination polynomial is easy. It's represented by our equation system, which is easy to encode in this polynomial H, which is given by Joos Heintz programming. Now, this is the following consequences that this makes it possible to prove that the main problem of symbolic multiplication of computer algebra to find to construct general purpose programs which resolve all elimination problems cannot be realized efficiently because the output, even if we admit the circuit representation for polynomials, may explodes. So, in other words, elimination has intrinsically exponential complexity correction, even if we change data structure, renounce on the representation of polynomials by coefficients and by circuit. So I want to explain this with redrawings from my life. First, in terms of learning, first, I consider the concept class of circles. A circle is a concept, and the class of all circles is my concept class. I say that circle is world, or I know a circle when I know its center and its radius. And learning is an iterative process. One learns from examples. The examples for circles are points on the circles, and now you know if three distant points on the circle, you can make a construction and you get the center and then you get the radius. Or if you want to do it analytically, you have the equations for the center and the radius in terms of three distant points. Then you form differences and you get the linear equation system which you can solve. Now, The following two drawings have the property that these points here, these red points, in both examples are the same, and these 4 points also are the same, but the figure which can give the figure which remains is different. See? You have something like that. So let us turn back to the first example. I suppose that this figure is the graph of one of my polynomials I exhibited you. So this is a polynomial. The hypothesis is a polynomial which is easy to evaluate. So this concept here has a short representation. Now, I choose once forever 7 random points and look on the corresponding point on my figure. These are 7 random points on my figure. So my theorem says that if I start from these random points, I have no chance to find a short representation of this figure, although there exists a short representation. But from these 7 points I can find this was the problem which I treated with the interpolation problem, and now here I have 4 regular points. I take the corresponding point on the figure and I take the projection. So I want to describe these projections, starting my computation from these points. The second example says this again goes wrong. And now if I make the correspondent, I take these 7 points and then take here one of these points and I say they are related. Then I can say I make the same construction for each of my figures. Then I may say that this point and these points are related if and only if there exists a point here, and if there exists such a figure which they relate. So my relation between points is maybe thought as a projection of a more general figure, and this has the effect that elimination tasks, description of elimination problems require exponential studies. So maybe since we are here in Argentina, there is a more simple paraphrase. That from French, from a researcher in social science, doing research about parallelism. And so he has to observe what parallelism does, has to classify the action, and has to describe in a book he has described in the book how terrorism acts. This book, Argentine says that foreigners are unable to do this. They will never understand terrorism. I will say this is wrong. He is able to write a book with an exact description from outside what terrorism is doing. But this page, this book will have 1,000 pages and he will not find an editor. On the other hand, a feminist to act as correct as feminist has not to read the book of 1,000 pages. Will never do it. Because he knows the internal structure of the feminism, which is hidden to the social surgery, which has obligation to get an objective description. He knows who is connected with whom, and with some very simple rules, he knows how to act in the same situation as here. This figure is simple to describe, but there is some hidden parameter. Even if you don't know this hidden parameter, it is impossible from only observing this figure to describe. So these results I explained to depend on some more or less deep mathematical results. And so I want to describe them. I need for that some language. First of all, let us consider a subset of C to the n, and the map of this subset to C to the n to C to the n. We say that this set is constructible if it's definable by a Boolean combination of polynomial equations. And there's the theorem of the 19th century that constructible is the same thing as definable using first order multipliers in the language of C. Then if I have a map from this constructible set to C to the n, we will say this map is constructible if the graph exists. And in particular, we want to say that this map is polynomial if it can realize by evaluating polynomial. Then there is another notion which is a little bit more complicated in the general context. We say that phi is rational. We require for that it's only a partial map, and these components are given locally by quotients of polynomial maps. One has to add some intermediates for that. Now, if I use gain elimination theory, I can prove that the map is constructible if it's piecewise rational. And now the crucial notions which I will use, I call this map constructible map P phi robust if it's constructible, I said it, and if it's additional continuous. This looks quite simple, but this has very deep consequences to us that it's additional continuous value. So an important property is that if I restrict a robust map, I have still a robust map. And what we did, we found a complete algebraic characterizations of robust maps. I don't write this characterization down, which requires some commutative algebra, but I shall use the following consequence of this characterization. If M is, for example, a smooth variety with my equations and smooth at each point, then a robust constructible map is also polynomial. This has some consequences for numerical computation. If we have if you take a numerical problem where we have an input space and an output space, constructible sets of approximation space of approximate solutions, and we have which from the approximate inputs computes approximating outputs with arithmetical operations. Then in numerical analysis, the continuity here is normally required. This means that the P is robust. And this has a consequence that if all points here of the approximate inputs are smooth points, then the computation at phi is also differentiable. So I spoke about, I used the notion of arithmetic circuit. I spoke about software engineering programmable algorithms, and so I want to make these kind of things a little bit more clear. Let me begin and determinate and constructible subsets of 2 to b bind space 2 to b r, and here the projections, the restriction of the projections to m. Now, by m parameterized arithmetic circuit is a device which is a direct acyclic graph where the nodes are labeled by the arithmetic operations. And it's a device which has this form. You see, here you have the input. You can, for example, add to input. You have a basic parameter node. You add to it a number. Then you may take, for example, the product of this result with this result, and finally you get an output. Now, we in difference to standard computer algebra, we want to use circuits, parametric circuits as data structures to represent polynomials. So polynomials are mathematical objects which are represented in the non-standard way. So for this purpose, we have to equip the circuit with certain semantics, and you see you have the nodes of the circuit labeled by an operation. So you have a evaluation procedure for the circuit which defines for each node a rational function. And this rational function we call intermediate result. Then our circuit has some nodes which are labeled as output nodes. These results we shall call binary result of the circuit, and then there are certain nodes which do not involve the variables or the input, which are called the parameter nodes, and the corresponding function are called parameters, and especially important are big parameters which are directly connected to a node which depends on the name. So at the end, beta is a syntactical object which we use to represent the final result. Now, for what I'm doing is very important, the notion of a robotic circuit. Here, in principle, we have only a rational map. For each node, we have a rational map defined by the intermediate results of the circuit, and then we suppose we have extended this rational map to a total map in a constructible way. And we call now the extension, the extension omega rho, which is parameterized algebraic arithmetic circuit. If each of the corresponding functions is a rho, so ultimately the rho. First of all, if there exists a robust extension with only one, so in this sense we can speak about robust circuits. Then we say that a circuit is totally division-free if we have only division by divisions by scalars, and essentially division-free. In our definition, we have made the hypothesis that our circuit is essentially division-free, that all nodes which involve inputs are only additions and multiplication, only parameter nodes involve division. So if the circuit is robust or intermediate results are polynomials if the variable x1 and the xn over the algebra of robust constructible functions defined. And as complexity measure, we use the non-scalar complexity measure. This means that we take additions and see linear operations as we can multiplications and divisions taken into account. Now, in the context of interpolation, we have the following result. If n and l are parameters, and e is 2 to the l, then we look at polynomials which can be evaluated with at most n non-scalar operation. So we look at the closure of the set of all polynomials which can be evaluated with L operations. These polynomials are of degree at most 2 to the L. So they have a high degree bound, and so they have many coefficients. Nevertheless, this variety has a small dimension, and this implies that there exists few points, k-many points, of small bit length, such that we can distinguish polynomials of this class, evaluating them in a few values. Such a sequence, I call it the identification sequence. Now, I want to present something which is more general than the concept of learning, and is well adapted to modelize the process of programming by software engineering rules elimination interpolation programs.
Would you recommend this quiz that you're going to present to a social worker that has power?
In just I modelize the action of the social research by investigation. Let me give you a constructible subsets of sum-affine space, sum-affine space, and two parameterized small robust surface which you could suppose that in some sense they are small, and which represent each one a polynomial. So theta prime the coefficient vector of these polynomials, and let omega O and O prime be the corresponding images. And the idea I have now that these images are geometrical objects which represent all instances of this polynomial. Now, as before, we suppose that there is a relation, a robust map between the class O and O prime, later I shall say that this is the abstract data type with another abstract data type, and I suppose that there is a proper robust map between them such that the diagram contains. Now I want to play a game on this situation. This is a two-party protocol with the quizmaster and the player. Player has unlimited computational power, and the quizmaster has limited computational power. Both quizmaster and player knows the circuit, but now the quizmaster chooses an element in U and hides it to the blind player. And the player can ask to the quizmaster a limited amount of questions about properties of H, U, and N. So these questions are not Boolean questions, but are questions which are answered with complex numbers. And from this data, so the player asks this question, and now we suppose that the quizmaster's answers depend only on the given polynomial H2, and then these answers are easy to evaluate for the quizmaster. So we have this origin diagram. Here is the U. The player asks questions, and the answers to these questions is imposed. It is represented by a map like this by a map like this in this manner where composition is easy to evaluate. Now we suppose that the player disposes over a small robust circuit, and that he is able to compute from the answers he received the parameters of the specialized circuit, and sends the circuit back to the quizmaster. Then the quizmaster applies the test I mentioned before to the new circuit and check whether the circuit you get from the planet evaluates a polynomial, binary polynomials. So the idea is to follow the parameter which determines the polynomial which one wants to evaluate is only going to increase mass, but later asks questions, and from the question he has to reconstruct a new circuit which represents the polynomial.
That's
5 minutes. Okay. Now the question is whether this can always be done efficiently, and the answer is that if you modelize the interpolation in this way, there is no efficient winning strategy, and also in case of elimination, there is no efficient winning strategy. Now, I want also to present an approximative model for this question, for this situation. We consider all polynomials in an arbitrary number of variables, and we can speak about this ring using addition, subtraction, and multiplication and equality. So if we look in this way at the situation, then any object we can represent is given by a circuit or by a formula. We say an abstract data type polynomials is a finite dimensional subspace of R to the R in the classes of objects which represent a consecutive subsets of C to the R in such a way that if I have here an abstract data type, I have here a class, then I have an abstraction function here, and I require that this abstraction function factorizes in such a way that omega is a polynomial function. This is the case when you look at circuit representation. So another thing I need is if I have two such representations, then I need to point to one high here. I am able to decide whether they represent the same object in the abstract data type. And to the consequences. What I explained or tried to explain has much to do with algorithm behavior in data. Here I have the graph of the function u, and we have of this function, we have a shadow function which associates us to such a here u is I have to say u is a parameter. Things which not have anything, but the presence see shadows of the function, but the functions function which whose value now depends on the representation only by the figure, and that the task of the presence is to reconstruct from the shadow what you see, the original representation of the figure. And so, if I translate what I explained now to this context, I get the result that prisoners unable to solve efficiently the task or any shadow function I have introduced. So let me say at the end what was my original motivation. First of all, let us observe that this polynomial is easy to evaluate by only ON operations, but this elimination, this is an elimination problem which appears from when analyzing the napkin problem. From this polynomial, nobody knows what is its complexity, and it is conjectured that it requires exponential time. In any case, if this polynomial is evaluated by polynomial number of operations, then the arithmetical hierarchy collapses. And if I change a little bit this example and consider these two polynomials, then I show with Ziewick a little bit more than a lot of time ago that both polynomials require exponential number of operations to be evaluated. Now, if I use twist games, I have I consider this polynomial, but I consider it analog in this way. Both polynomials require 2 to the n operations. This means that the situation which I was originally interested in, this one, is something somewhat finer of what I'm able to prove at this moment. So I cannot prove my original result, but in any case, what I can prove is hardness of probability, and this suffices to prove the hardness of elimination. So I think maybe thoughts went in the same direction.
Okay, thank you. There's 2 questions, but not one to them because I don't want to be behind speaking. So,
maybe I can ask a question. know the answer because you told me, but I want to have. What kind of everyday class of polynomials that are easy to evaluate, but hard to learn or hard to get the definition? So because you showed it in three classes today.
In general, the examples of the Japanese structure they are artificial. So I can my construction, my argumentation work exactly for this what I can say is that if I didn't find myself elimination procedures which are implemented respecting the rules of software engineering, then what in general is happening, that you obtain long representations of elimination polynomials because certain conditions or certain considerations, like in this case, occur very often.
If I give you a polynomial and say, can you tell whether it's going to be?
No, I only ask a question.
This is a big problem.
Okay, thank you.